Alrighty. Let's take a look at page 73. We're going to take a look at our next section. Maybe before we get started on that, are there any questions you guys want to go over from the homework? The composition stuff we were doing yesterday? No? We're good to go? Alright, so we're going to start our last section of this unit today. We're going to talk about, this is probably going to be new to us, okay? I'm pretty certain that we haven't really heard of continuity before, or discontinuities. Do those words sound familiar? Oh, maybe they do. Perfect. Okay, maybe they do. It's okay if they don't. We're going to discuss what makes a graph discontinuous. Meaning, if you were to draw the graph, you would have to lift up your pencil at some point. Okay? Continuous means like, I don't know how you phrase it, continuous. It just goes on. Okay? If it's discontinuous, there's some point that's not located on the graph that we'd have to pick up our pencil to kind of go over. So we're going to take a look at those ideas today. Okay? Discontinuities. To introduce this, we're going to take a look at 3 scenarios. We're going to take a look at 3 possible graphs, and then we're going to classify them as either continuous, we can draw them without lifting up our pencil, or discontinuous. We would have to lift up our pencil at some spot. Yeah, sure. Okay, so our first one we have here is we have pieces of a graph, kind of like the left side and the right side of a graph, that connect at a closed circle at some specific x value. So on the x-axis, let's go ahead and label this location that we're focusing on. Okay, we're going to use the letter A. You can let A be whatever number you want, but we're looking at somewhere on the x-axis. We're told we have a closed circle at that point, so I don't care where you put your closed circle. Okay, above A, below A, whatever. It just has to be somewhere at that location. And we have 2 pieces, meaning the left side of this point and the right side of this point connecting each other. So I don't care what kind of graph you draw. We'll draw a left side and a right side of that point. So based off of this graph, okay, this scenario, if you were to draw the graph from left to right, would you ever have to lift up your pencil? No. Okay, you can always touch the left-hand side. You're clearly going to touch the point because it's closed, and as you continue your pencil, you'll go to the right forever. Okay, so this is what we would say is a continuous, we are continuous at this specific x value of A. Okay, we can draw our graph without lifting up our pencil at that point. We're going to take a look at some other cases though. The middle one, let's say we have that same x location. The pieces connect at an open circle. Okay, so something like that. If you were to draw the graph from left to right, would you be able to draw that graph without lifting up your pencil? No, right? You would draw the left. You would have to lift up your pencil to go over that circle because technically there's no graph there, and then you could continue on the right-hand side. So since we had to lift up our pencil, this is what we would say is a discontinuous graph at the x value of A. That's the specific location we'd have to lift up our pencil. So far, so good? We see the difference between continuous and discontinuous? Okay, let's see, our last one, the pieces cannot connect with each other at A. So maybe we have some graph to the left, but the graph to the right does not connect. So at this location of A, sometimes you can have two open circles. Maybe sometimes you have one open and one closed. Okay, that's a possibility as well. They'll never both be closed though. Okay, because if they were both closed, that wouldn't be a function, right? It wouldn't pass the vertical line test. You'd touch the graph twice. So they're either both open or you have one of each. That doesn't really matter that much, okay? If you were to draw this graph with your pencil left to right, would you have to lift up your pencil at some point? Yeah, you'd have to draw the left-hand side, pick up your pencil, move to the other graph so you can keep going to the right. So this is a discontinuous graph at that x value of A. That's where you'd have to pick up your pencil. So we have a clear picture of what continuous looks like, but notice how we have different options as to what the graph might look like if it's discontinuous somewhere. Okay, so we're going to first explore a continuous option on the table on that page, and then we're going to dive into the discontinuities. Okay, maybe we have an open circle where they connect. Maybe we have some type of jump where they don't connect. We're going to explore those options. Okay, so let's go ahead and take a look at the chart at the bottom. Most, if not all of the equations we're going to look at in this section are piecewise. Okay, we're going to have different equations showing up at different locations, okay, certain sections of the graph. So before we get into some of the questions, let's get a picture of this guy, okay, see what it looks like. We talked about graphing piecewise functions earlier this year, so we should be able to do this. How might you guys want to start graphing those two equations? Yeah. Let's graph the constraints, aka your domains, okay, those x values that you're able to plug in. So we'll draw a little barrier at -5 and at 0. Again, those are not asymptotes. They're like fences, barriers, walls, however you want to phrase it. The first equation is going to show up between -5 and 0. The second equation is going to show up on the entire right-hand side, which means we have nothing going on the left. So now that we know which equation is going to show up where, how can we start to actually graph these equations or these different pieces? Maybe we'll start with the first one. How might you want to graph that quadratic? We have a power of 2. Can we get some points to help us graph it? Where can we get the points from? Yeah. We're going to plug in those domain values, like the beginning and the ending ones. Okay, so if we plug in -5, -5 plus 3, we got -2, -2 squared, +4, negative out front, so it becomes a -4, plus 4 on the end, we got 0. So let's plot that point, x value -5, y value of 0, open or closed point. I heard closed, right? We have that equal sign, so we can include that point. Let's do the same thing for the other constraint or domain value. If we plug in 0, we'll have 3 squared, which is 9, negative out front, so -9, plus 4, we get -5. Open or closed circle? Open, good. All right, so we have to connect the dots somewhere between those 2 points. Can we determine maybe what shape this graph should look like first? So we have a right idea. This is a quadratic. We have a power of 2. So what should the graph look like? Yeah?
Hyperbola.
Close. Parabola.
Oh, yeah.
It's okay. A hyperbola is a crazy looking shape. Okay. A parabola, a U shape. So we need some type of guiding point in the middle to help us figure out where is the top of that U or the bottom of the U to help us out. How do you think we can figure out that point? The vertex. Okay, the top of the U, bottom of the U. Where might that come from? Yeah. Let's use the translations. All right, so do you notice any movement left or right going on in that equation? Good, Nate?
It's going left, right?
Left 3. Okay, so that's an X location. Okay, left or right, that's an X. Left 3. You want to do another one? Up 4, that's a Y change. Okay, up 4. So instead of the vertex starting at the origin, we now moved it left 3, up 4. We can plot that point, and notice how it's in the correct section of our graph. So everything's checking out. So if this is the vertex, this would be the top of the U because we would have to connect it with the other 2 points we have. Coming back to us a little bit? Perfect. Okay, let's try the other one. So if we get some points, we only have one value for this one to plug in. If we plug in 0, we'll have the absolute value of -2, which then changes to +2. -7 would give us a -5. So if we go to that point, 0, -5, it's an open circle already based off the parabola graph. But this new point we need to plot, is it going to stay open or closed? Yeah.
No. Actually, I have a question.
Yeah.
Did you say the answers can't be negative if it's an absolute value?
You cannot have an absolute value equal to a negative number. But what's happening here is, notice how this absolute value was positive. It was 2, and it was after the absolute value that it became negative. So after is okay, but you cannot have it as an answer initially. Does that make sense? Okay. All right, so 0, -5 is already there. It's open. This is telling us it needs to be closed, right? Because we have that bar. So what do you think we're going to do to that open circle? If it was open and now it needs to be closed, we're going to fill it in, right? This is now a closed circle. So we only had one value. We need another point to kind of guide this graph for us. If this is an absolute value, what shape should we anticipate? A V. Good. Okay, so just like the other one, let's go ahead and figure out where the bottom or top of this V is. Can we tell based off of those transformations, left or right, up or down, where this bottom or top of V is? Down 7. Yeah. Right 2. All right, so let's plot that point. So if that's the bottom of the V, we're going to have a little segment on the left-hand side connecting that dot. But we said the right-hand side is going to continue forever. So we're going to make sure we have an arrow there. Looks really good. So now that we have a picture, we're going to use the graph to help us answer some questions, but we're going to eventually think about what if we didn't have the graph? Okay, what if we just had the equations? How could we still figure out if this is continuous or not? Let's answer that question based off the graph. If you started at that beginning point and you drew it with your pencil, would you ever have to lift up your pencil? Yeah.
Yes.
Where?
At the 0, -5.
All right, so it was open, right? But didn't we fill that in?
Yeah.
Isn't it now a closed circle?
Yeah.
Okay. So it initially was a point you'd have to skip over, but this other section filled it in, which means you can keep going.
Okay.
Does that make sense? Okay. So if you started here and you drew this, but this is now closed, you can continue to draw without lifting up your pencil. So we know this is a continuous graph, okay, just by the picture. We're eventually going to think about what if we didn't have the picture to help us out. But before we get there, let's check this out. The first piece of the graph will end just shy of what x value? So this blue graph, where does it end in terms of the x-axis? What's the last x value that you notice? Yeah, 0. Okay, so you can tell that based off the graph. Notice how the blue graph stops at that x value of 0. You can also tell based off the equation, right? Isn't 0 the last value in the domain? Okay, the second piece will begin at which x location? So where does the red graph begin on the graph? Maybe you can tell based off the domains from the equation. Where's the second one begin? Can you see how it's the same 0 value? Right? Okay. So this location of 0 is kind of interesting to us because that's where one graph ends and one graph begins. In order for us to be continuous, if one graph ends there and the other one begins there, we have to make sure that they match up. That way we can draw it without lifting up your pencil. If they don't match up, isn't that going to be discontinuous? You'd have to pick up your pencil. Okay? So we are very interested in where one graph ends and one graph begins. Okay, we're going to analyze that location. So speaking of this x value of 0, is that x value defined? In other words, is there an equation you are able to plug in 0 into? Can you tell based off the domains? Are you able to plug in 0 somewhere? I see some head shaking, yes. Which equation can you plug in 0 to? Go, Cole?
The absolute value.
Why?
Because the constraint is greater than or equal to 0.
That's the one you equal 0. So that's the one you can actually plug it into. So let's go ahead and figure that out. If we were to plug in 0 into that second equation, okay, that absolute value, what would we get out? Did we already do that? We got -5. Okay, so since you are able to plug in 0 and you get out that -5 answer, that means graphically this should be a closed circle, right? That point exists, it's defined. And notice how that makes sense because we said the red graph was a closed circle that would fill in the blue open one. Okay, let's go ahead and check out this notation, a little bit new. So if you look at the next box, I'm going to read this out loud so it kind of sinks in. It says, as x approaches. That arrow means approaching. So as x approaches 0, do you guys see that little kind of negative in the exponent spot? It might be a little faint, but can we see that? Yeah. Thank you. Okay. That little negative in the exponent spot means from the left-hand side. So very similarly, if you have a little plus in the exponent spot, that means from the right-hand side. So what we're going to do is we're going to take a look at this graph, because we have a picture of it, and if we were to trace the graph on the left-hand side of 0, we want to figure out what is the graph approaching, meaning what is the y value that the graph is approaching. So here's that x location of 0, where one graph began and the other one ended. Okay, that's kind of our barrier. If you were to trace the left-hand side of that graph, getting closer to that barrier of 0, what y value does it look like you're getting closer to? Can you count it? 1, 2, 3, 4. Looks like -5, right? Let's try the same thing on the other side. So as you trace the right-hand side of 0, so that would be our red graph, okay, getting closer to that barrier, what y value does your graph get closer to? -5 again. Okay, so let's go ahead and take a look at this. The left piece was approaching -5, the right piece was approaching -5, and notice how we had a closed circle at -5. Of the three options at the top that we looked at, which one do you think that is kind of resembling? The left side and the right side are approaching each other, they're meeting up, they have the same value, and you have a closed circle. Which one does that kind of look like? Go, Cole?
Continuous.
It's continuous, right? And didn't we already say this should be continuous? We could draw without lifting up our pencil. Notice how this analysis is confirming that. Okay, we're showing the left-hand side and the right-hand side meet. Okay, they have the same y value, the same height, but we also happen to have a closed circle there, which means we can continue our graph through that meeting point. Okay? Now let's try to amp it up a bit. Let's say we didn't have the graph. Okay? No picture. All we had was this equation. How could we still figure out this -5 value? What do you think? We're going to plug in 0 for both of them. Okay, so let's check this out. As x approaches 0 from the left, which equation should we use to symbolize the left-hand side of 0? Again, you're not given the graph, so you got to take a look at your equations. Which one shows up to the left of 0? Yeah. The quadratic, right. If you take a look at your domains or your constraints, x values to the left of 0 are all negative. Okay, so let's go ahead and plug in 0 into that quadratic. 3 squared is 9, negative out front becomes -9, plus 4. Notice how we get the same -5 value algebraically, okay, by hand, as we did from the graph. So that checks out. We also have to check the right-hand side because we got to make sure both sides are meeting up. If they're not, that's an issue, okay, because they're not going to connect. We got to check both sides. So that would leave the second equation to represent the right-hand side. Let's plug in 0 there. We'll get 2 minus 7, which is the same -5. So either based off of a graph or just based off of equations, we can still figure out what the left side is doing and what the right side is doing. Okay, so let's go ahead and make a formal statement, okay, because we said that the graph is continuous at this x value of 5. Okay, let's go ahead and say why. The graph is continuous at this x value of 0. Remember, that's where one graph ended and the other one began. Because, what might you want to say? Okay, so that's how I want you to think about it. That's how I want you to think about it. That's not bad, Isaiah. Okay, that's how I want you to think about it. But mathematically, okay, what's going on? Why do you not have to lift up your pencil? Yeah.
Does the lines meet?
The lines meet. Okay, because the left and right sides meet. That's part of it. There's one more piece. At a closed circle. Right. Because if you take a look at the top, okay, those three options, didn't the middle graph, didn't they meet, right? But they met at an open circle. We said that was discontinuous, okay? The only way you can explain continuity is that the two sides meet and they meet at a closed circle. We have to check those two ideas, okay? Let's go ahead and take a look at some discontinuities. These are the ones we're really interested in. Okay, what if we have to lift up our pencil? So on the front, we had two different options. We kind of had the two sides meeting at an open circle. Maybe we had the two sides not meeting at all. Yes, ma'am. Sure. Okay, so we're going to define these two different types of discontinuities. Our first one is what we're going to call a point discontinuity. Sometimes you might hear me refer to it as a hole, because there's literally like a hole or a chunk missing in your graph. And a point discontinuity is defined as, we'll say, two pieces connect at an open circle. Do we know what this other type of discontinuity is called? Some of you shook your heads that you've heard of discontinuities before. I'm wondering if we know the types We have a hole discontinuity, or maybe you haven't heard of it. Okay, this is what's called a jump discontinuity. It kind of makes sense because if you were to draw that graph, you'd have to literally jump from one equation to the other with your pencil. Okay, so a jump discontinuity has two pieces that do not connect at all. Again, you can have two open circles, maybe one's open, one's closed. You'll never have both closed though. Okay, so what I want to try to do is take a look at these four graphs on the page and try to locate where some of these discontinuities are. So if you take a look at the first one on the top left-hand corner, can you identify an X location where there's a hole or a jump based off of our definitions? What do you think, Cole? 3. Okay, so if you were to draw this graph, you would have to lift up your pencil at 3, so that means it's discontinuous. Can you determine which type it is, perhaps? Do we have two pieces that connect in an open circle, or do we have two pieces that don't connect at all? Yeah, it's a jump. So we would say we have a jump at the x equals 3 location. You're telling me exactly where it is. Notice how you have two open circles there. What about the one below it? If you were to trace that pencil or that graph with your pencil, would you have to lift up somewhere? Can we find a discontinuity?
-1.
-1. And can you classify it?
A point.
A point or a hole. Okay, you can use either one of those words. I'm used to using hole. Okay, hole at x equals -1. But sometimes you'll hear it referred to as a point discontinuity because technically there's no point there. What about the next top one on the right-hand side? Where would you have to lift up your pencil? Can you tell me the spot? -3, okay, and what type? We got a jump. Notice how this was a jump that had a closed circle and an open one. Okay, that's another possibility. What about the last one at the bottom? If you had to draw it without lifting up your pencil, could you or would you have to lift up your pencil? What's going on? Yeah. Okay, so if you trace the left-hand side, you're good, but I eventually reach a point where there's no graph, so I'd have to lift up my pencil to come down here for the closed circle, and then I'd have to go back up there to continue. So there is a spot where you have to lift up your pencil. Question is, what type is it? Is it a hole or is it a jump? Look at your definitions. Do you have two pieces connecting in an open circle, or do you have two pieces that don't connect at all?
They don't connect at all.
Are you sure? Are you sure? Yeah? You don't think if you were to continue the left and the right side they wouldn't match up?
They do not connect.
They would connect, right? If that point was filled in, right? They would connect, but unfortunately it's an open circle. Okay, this is a hole. If you take a look at your two pictures up here, okay, a jump, you have one section on the left and a completely different section on the right. Okay, a hole is like a regular graph with just a chunk of it out. Okay, a hole or a piece is missing. That's kind of what's happening here. Hole at x equals -3. That one's a little tricky because we did have that extra dot down there. Okay, but it's still a hole. Do you think we can identify the discontinuities? Not too bad? All right. Let's take a look at our first analysis. Okay, take a look at page 75. What we're going to do, we're going to focus on these four different graphs that we just identified the discontinuities for. Okay, The first one we're going to look at is the F graph. So what I need you to do is not only have this F table in front of you, but also make sure you can see the F graph from the other page. Okay? Okay, so we're going to take a look at this graph to help us fill out this table. Okay? So taking a look at the F graph, what type of discontinuity did we say it had, and where was it? Jump at the x equals 3 value. Okay? We're looking at the F graph, top left-hand graph on the other page. Okay? Is the function defined at that x equals 3 value? No. How can you tell? I'm going to bring it up here. How can you tell that there is no point at 3? Yeah.
It never actually touches the 3.
Okay, so there is no closed circle. You could say that. How could you tell based off the equations? How could you tell there's no closed circle at 3? Yeah. There's no equal bar under those 3 values, right? Okay, so in either case, we have no closed circle at 3. So is it defined? No, because there are no closed circles at the x value of 3. So based off of that, can we already determine if it's continuous or not? Probably, right? Because we said to be continuous, both sides have to meet up, and they have to meet up at a closed circle. Clearly, we don't even have that. So we already know it's discontinuous. Okay, so that's a good piece there. Take a look at the next one. By investigating the constraints or the domains, the first piece of the graph just stops shy of what value, and the second piece begins at what value. Okay, so graphically speaking, where does the first equation end and where does the second one begin? Can you tell based off of the domain values? Or maybe looking at the graph. The first equation goes from -8 to 3, and the second equation kind of starts at 3 and goes on forever. So the first one ends at 3, whereas the second one begins at 3. Notice how that's the interesting spot because that's where our jump was. Okay, where one equation's ending and the other one's beginning. All right, let's analyze the sides, okay, from the left and the right. If you take a look at the graph, here's that x value of 3. If you were to trace the graph on the left-hand side, what y value are you getting closer to? Two, right? If you trace the left-hand side, you're getting closer and closer to that open circle, which has a height of 2. Let's check out the right-hand side, okay? So trace the right-handed graph towards that x value of 3. What height are you getting closer to? 4. Okay, so let's think about it. Don't look at the graph for a second. Okay, think about what these numbers are telling you. If the left side has a height of 2 and the right side has a height of 4, okay, left side, height of 2, or it's backwards for you. Left side, height of 2, right side, height of 4. What kind of discontinuity is that? It's a jump, right? You can see that if you visualize it. Without even looking at the graph, that's what the numbers are telling us. So we have a jump discontinuity, just like we said we should. Okay? Let's see if we can get those same values by using the equations. So if we were to approach this 3 value from the left, which equation would we use from the function? You have to take a look at the other page. Which one shows up to the left of 3? Yeah. Absolute value, what are you going to say? The absolute value one? Perfect. Okay. So let's go ahead and plug in 3. into the absolute value equation from the other page. Let's see, we'll have the absolute value of 6, which is 6, minus 4 is 2. Notice how that confirms what we found graphically. So no matter if you have a picture, no matter if you just have an equation, you can still figure out what the left side is doing. Let's go ahead and check the right side. Okay, so as x approaches 3 from the right, that would be our other equation. So let's plug in 3 there. Negative 1/3 times 3. The 3's would cancel, so we're left with negative 1. Plus 5 gives us 4. Notice how we had the same answer based off the graph. So again, whether you have a graph or whether you have an equation, you can still figure out what both sides are doing. Okay? So let's formally say this, okay? The graph is discontinuous at this x value of 3, okay, where one graph ends and the other one begins, because why? Yes, you would have to lift up your pencil, but what is causing that to happen? How do you want to phrase it? What do you think, Isaiah? The two graphs don't touch, okay? The two sides don't meet, something like that, okay? Because the two sides don't meet at the same point, okay? If they're not connecting, there's no chance in heck that it would be continuous, okay, because they're not even having a chance to go from one graph to the next, okay, in terms of your pencil, okay? And we see that. Notice the left approach 2, the right approach 4, those are not meeting up. Does that make sense? Graphically, we have that jump or that separation, okay? Tomorrow, we're going to take a look at the same analysis, but for the other 3 graphs that we discussed before, okay?